Hello and welcome to HBase on EMR. Today I want to make sure that we cover a high-level introduction into what is Hadoop, what is HBase, what is Amazon's electric MapReduce, why we want to run HBase on a cluster, getting into some sample code, and then kind of running into conclusion and being able to show you how to learn more information about Hadoop, HBase, and of course Amazon. My name is Mike Siegel. I am a principal consultant with Think Big Analytics. I have been working primarily with Hadoop and HBase since 2009. Whenever I've had to discuss with people what Hadoop is, the best and simplest explanation I have is that Hadoop is an open source framework for parallel processing. We start looking at the components of Hadoop. We start looking at the ecosystem. Here we see that we have the Hadoop file system, which is a distributed file system so that data can be shared across every single node in the cluster, so that one machine may actually hold the data, but another machine somewhere else in the cluster has the ability to read and fetch that data as if it were on its own machine. We then start talking about the MapReduce, and that is a distributed framework for executing work in parallel. This allows us to basically take a problem, break it down into parallel tasks, and on each of those parallel tasks simultaneously, so that if we have a problem that runs in 100 minutes, and we have 100 tasks that we can break it down into and run in parallel, we should be able to run those tasks within 1 minute or so. It's not 100% efficient and break down, but just to prove a point that if we can take that job, a long-running job, and break it down into parallel tasks, then we can run it in as long as it takes to run those parallel tasks. Well, what's an elastic MapReduce? Basically, the simplest way to describe it is EMR is the Hadoop on the cloud. And that is, its EMR, Elastic MapReduce, allows us to spin up, run a Hadoop cluster on Amazon's hardware, so it's virtualized, running out there, pulling data in and out of their environment, and then being able to take our tasks and take our results, either store it in staying inside Amazon's or bring it back down to our local center. Currently, there is roughly 2+ million clusters we're running in 2012 with over thousands of customers. Here's just a handful of some of the more prominent people running their applications in their environments in Amazon. As we can see, there's some very big names, notably Netflix, the New York Times, as well as NASDAQ. But how does it really work? In Amazon, the core component is their S3 file system. This is a very large file system that has HDFS running on top of it. It's where customers can upload all of their data and have petabytes of data up out there. As they need to, they can spin up small clusters, shown here, if they have to, and then also if they need to take that small cluster, they can on the fly resize that cluster as needed, and then bring it back down as needed as well. But also they can run clusters, both two clusters simultaneously against the same data stored in S3. I want to point out that what the flexibility of being able to expand and contract your clusters is very important for customers such as retailers, where the bulk of their business is done in 2 or 3 months at the end of the year, from Thanksgiving, known as the day after Thanksgiving, known as Black Friday, through January 1st, where it takes them through Christmas and returns. During that time, they're going to need a lot of power, and they can use the power that they have. That they can always expand the power that they need for that time period. But then when they don't need the power, they can resize and use less, so they're more efficient. Now that we're coming into April, coming up for April 15th, tax day, same thing can be said for accountants and accounting firms, where they may need to do more number crunching. They can spin up a larger cluster. Then once the tax season's over, they can spin down to their base necessary needs. But what is HBase? When we go back to our Hadoop ecosystem, first I'm skipping Hive and Pig. These are languages that, again, are used for sequential and batch processing, where they're able to do transformations on the data that's sitting out in the flat file system. They can also actually access data sitting in HBase, but HBase is a NoSQL non-sequential data store. And getting into a better definition, HBase is a NoSQL database. It's column-oriented in design, highly distributed, highly scalable, and to another phrase, another explanation that probably work best for object-oriented programmers is that it's a non-relational persistent object store. If you are going to buy any book describing HBase or learning about HBase, Lars George is the author who wrote HBase: A Definitive Guide. It's an O'Reilly publication. This is probably the best resource, and I urge you that to get this resource if you're seriously looking to learn about HBase. It tells you everything you wanted to know about the internals and then some. It's definitely the resource that everyone refers to in terms of explanation of how something works and why you should do something a certain way or not. Let's talk about what HBase isn't. HBase is not a relational database. It doesn't support transactions. It's not built on a traditional updatable file system. HDFS as a file system it allows you to write once and read many. It doesn't allow you to open the same file and read it multiple times. That's a big difference from traditional Unix file systems where you can open a file and write and append. It's also not really a standalone system. While it's theoretically possible, I really doubt that people would choose to run HBase as their primary database outside of the Hadoop environment. And that's because it's not the only NoSQL database out there. There are many other databases that are NoSQL that are better fit for standalone operations. If we want to take a look and compare relational databases versus HBase, we can take a look and go down the list. And the first thing that comes to mind is ACID versus HBase not having ACID compliance. ACID is actually an acronym for atomicity, consistency, isolation, and durability, while HBase has similar features to allow it to function. It is not ACID, and that's a very important distinction. Where we see in traditional relational databases the term of sharding or data partitioning, HBase has a similar function in distributed regions. And that is to say that at every single node in a cluster, you can set up a region server that manages different regions. So your data is spread across the cluster so that you have better access and faster access out there. Relational databases have a SQL language. By default, HBase does not. It is primarily a key lookup or key range scans. And it's all done through programmatically through Ruby or in that case, JRuby or Java. Relational databases have triggers and stored procedures. Recently, HBase has added coprocessors. They have the similar type functions. Coprocessors are very, very new, and while they exist for the novice or somebody who's just starting with HBase, it's strongly urged that they not use these systems until they are more familiar and have come up to speed with HBase. It's still something that is an advanced feature that it's not recommended for individuals who don't really have a good understanding of Hadoop and HBase. As we go down the list, we see that relational databases do have indexes. We talk about the B+ tree and R tree for geospatial data. HBase by default has no indexing. However, there are ways of adding indexes to HBase, and there are third-party people trying to add and create indexing there. Relational database, again, is highly normalized. We see primarily third normal form and taking advantage of relational math with some denormalization in data warehouses for better performance. HBase is completely normalized. It works best when you flatten out relational data, or you work with data as records and not follow a relational model at all. The relational database has built-in primitive data types. You can see dates, decimal, money, your integers, floating type, as well as strings or character arrays. All HBase has are byte arrays. This is probably one of the things that makes HBase so powerful in that you're able to sort everything as a byte array. You have one data type, and it lets you add a third dimension to your data model. Within a relational data model, the relational database, you have in-place updates. That is, I can update a record, and that specific instance of the record is updated. There are no other copies. With HBase, you have cell versioning within a column. So why do we want to look at HBase over a relational model? First, it handles unstructured and semi-structured data very well, whereas a relational database cannot really handle unstructured data. It handles large data volumes. HBase can handle petabytes. Relational databases tend to die out after hundreds of terabytes or tens of terabytes. Excuse me. HBase is very, very flexible. It allows us to access it via ad hoc queries, so I can fetch an individual record, or I could do a full or partial table scan. So I can scan with a start row and stop row and get just a subset of data, which we'll show later on, or I could do a complete scan of the full table in a MapReduce. It's very cost effective in terms of scalability. It's near linear in terms of scalability. And this is kind of a critical thing, is that if I use get, which is to pull a single record passing into key, I get one result set back. If I have 10 nodes, it takes X time. If I have 100 nodes, it should take X amount of time as well, the same amount of time. If I have 100 nodes, 1,000 or 200 nodes or 500 nodes, it's still going to be consistent in terms, or give or take a little bit, in terms of pulling out that data. So we have near linear. So the time amount it takes to pull out a single record is going to be consistent as the cluster grows. The biggest strength of HBase is that it's part of the Hadoop ecosystem. And that is to say that when you download Hadoop or spin up an EMR cluster, you have the option of starting up HBase as well. Wherever you have Hadoop, you're going to have HBase. It's a component of it, even though it is a separate high-level project under Apache. It's in terms of NoSQL. Its strength is the fact that you have data locality on the cluster, so when you run a MapReduce job, in parallel, you're going to run your jobs against data that's going to be local and doesn't have to be shipped from an outside source. Really jumping ahead is that we don't really have enough time to do a deep dive into HBase, getting into some of the structures, or getting into how to use it effectively, how to do schema design. At Think Big, we do teach a 2-day course that's Introduction to HBase. We actually teach it using Amazon. And rather than give you a boring slide deck presentation, I want to start getting into some fun and show you how HBase is in action, how it works. So we started looking at HBase on EMR. The first thing we have to do is set up a cluster. I myself prefer well, you do have the web GUI. I myself really prefer the Ruby command line, or Amazon calls it their CLI. There's a small program starts off called Elastic MapReduce, which is a script to launch the cluster or run commands against the cluster. Most of the time, we recommend just aliasing it to EM, so that's a simpler and easier to type. HBase requires a X large instance or higher. In this case, we've actually been able to start with high 4XL in terms of cluster size, which was just announced last week. We have a samplification here where you can see where I call Elastic MapReduce. I create it, I keep it alive, I specify the instance. Because of our account, I've only limited to number of 2 instances, and also the fact that in this example, we're not doing a lot of data, just enough to show what's going on. I also, in addition to running HBase, I also by default start up Pig and Hive. Again, the exciting thing is that this HI large, high 1 large, high 1 4XL, as I like to call it, is brand new on EMR. It's been out on EC2 for a while, but it's now part of EMR, and it allows us a lot more memory and a little bit more disk than the standard cluster, which makes it easier to start up Hadoop. Now that we have basically a sandbox out there, we want to define a table to store our data. We need to basically load the data into the sandbox and work with. That's going from it's going from S3. And then once we have HBase, we need to do something with that data. When we're done, we want to put that result set to S3. So this is really outlining the two sample code piece of code that we have, where I'm going to pull out data, and I'm going to use a data set coming from, actually, believe it or not, InfoChimps, which has the stock data for all of NASDAQ, I'm sorry, not NASDAQ, all of New York Stock Exchange and Amex from 1970 to 2010. And by this, it's all the stocks being traded, their day close, volume, high-low range of that day. And again, that's quite a bit of data. It's roughly uncompressed 2 gigabytes of data, and for a sample and on a 2-node cluster, that's quite a bit. When I actually created the cluster, this is the actual string that I used. I go back to that, I apologize. One of the things is that because it takes time to start to spin up the cluster and run this, rather than have dead space and dead time, I've actually pre-launched the cluster, but this is what I used to start it. I wanted to point down to the fact that I'm using a bootstrap action to increase the number of map tasks and reduce tasks to 6 and 6. By default, the Amazon EMR cluster starts up with 1 mapper, 1 reducer per node, so you don't get a lot of parallelism. Because these 4XL large nodes have more disk, more memory, faster disk, we're able to increase the number of parallel tasks that we can run on a cluster. So while they're a little bit more expensive because they're a much more powerful machine, we tend to be able to tune towards that. This is just the base number. This is just a very, very simple change. Ideally, if we were going to be doing more work, we would be wanting to tune the Hadoop cluster and HBase more than just the simple mappers and reducers. So really, we want to take a look at some of the sample code. The first problem is loading HBase from S3. So for this example, as I said earlier, we use the data sets of all the New York Stock Exchange and Amex stock tradings from 1970 to 2010. We did this with the data being sitting on an S3, and to launch the job, we ran this invocation where basically it's a standard in Hadoop. You basically specify Hadoop jar, you pass in the jar that you want to run, you then pass in the Java main that you wish to run. In this case, it's com.thinkbiganalytics.academy.stock HBase loader. One of the parameters for that jar is to have a tutorial properties so that we can specify information that's going to be cluster specific. At the same time, we specify where we're reading the data from, the input directory, and that's the S3 bucket, and then the output directory on the cluster, which really just has some output job data if it exists. We're attaching and placing the code out on S3, so at the end of this presentation, there will be an announcement as to where the code can be found publicly, along with some basic instructions on how to start and set up the cluster. Everything that I've done here for this presentation, you should be able to do on your own using that information out there. A couple of things I want to point out is that we also use the new APIs, which is MapReduce classes, not the MapRed classes. This is primarily for the sense that it's a little bit cleaner and neater to use, whereas the older MapReduce may have more features, functionalities. The MapReduce classes, the newer classes, are the quote-unquote new Java API, which has been around for 3 years. gives you what you need in a minimalist format. And as time goes forward, I believe there's more of a shift to using the new APIs. Here, we use a tool runner to launch the jobs. In this, I cut out from the code 3 main lines or sections. We can see that basically the class definition, in our case, our main class is stocks HBase loader, but it really extends configure and implements tool. Tool is a interface that has specifics where you have a method of run. So that when you get down into your main, which we have down here, it's very, very simple. All we do here is we take in the arguments that are passed in on the command line, and we tell the tool runner run, which is basically to run this class, passing in the arguments. And then at the end, we just exit. So our main app, essentially our main code is very, very small. Then we start getting into the run. I won't show you the entire run application. That's where the meat of our application is. But basically, it's a public int run, and all you have to do is throw exception. And then inside this method, we then set up the cluster, we set up the job, and then execute the job. And as we look at the code, you can see exactly what we're doing, the steps, and how to set up the job. The key here that I want to show is that we're reading from S3. We're not the local cluster. So here in our file input format, we want to set a URI, a Universal Resource Indicator or Locator, of the path. So our path is not a local file system path or string. So the only change we have to make to run this in EMR, pulling from S3, is to use to take the string and turn it into a URI and generate a path from it, versus just taking that string and running a path from it, or creating the path from it. That's not a lot of code change. And again, this is only if we want to use S3 as our input or as our output. That's the only difference in this code if we're going to run it on a local cluster or if we're going to run it EMR and pull data in and out of S3. For the mapper of this class, basically we have a very, very simple mapper. In the class itself, we have a class level variable, which is the reference to the H table. This is how the data is being able to be written to the H table. In our setup, we actually go through our configuration, and we instantiate that configuration. We use that to make a connection to the H table, think big stocks. Once we have that, we're going to use that for the entire life of that mapper class. So in a MapReduce job, when the job gets launched, the mapper is then started on every single node in the cluster, and it is passed in it's instantiated, and it's passed in all the information to start up and run. As data is pulled from our source, it then in mapper.map, which we have in the next section, is what processes each line of the file or each line of the input from wherever that source is. In this case, we're passing in obviously a key and a text value and the context. Because we're not actually writing out to anything, we're writing out to HBase, we actually just use inside that mapper.map method, we actually then use a put statement to then put it to the HBase table. At the very end, obviously, we have cleanup, which basically tells us we want to, we're all done, we're finished running the mapper job, we want to, the mapper task, we want to then tell the HBase table to close this connection, which does the automatic flushing, so everything is cleaned up and done. If you notice, all of these are overrides because we are overriding the base functions inside mapper, the underlying mapper class. Now, the reason I've actually gone through the code like this is because the process to load the gigabyte of data, or actually 2 gigabytes of data, takes about an hour to run on this small cluster. If I had more nodes, obviously it would run much faster, and I don't have the ability to do that in real time. Even if having people sit at a blank screen and watch it work. But to show you that it worked, We start off, and again, I apologize if this is a little bit small on the screen. We can see that basically with the start of the job, at 23 minutes into the job, how it's running, we can see that we have actually processed in the map input records 3.5 million records. We can see that we have on this cluster, we're running 6 tasks. We've completed 3 tasks already, and we have 136 more tasks to go. It's important to note too that by default we have 10 reducers set. In this application we do not have a reducer, so what will happen is it'll start the reducers and they'll do nothing. The next slide basically shows during the load process how the cluster works. I should say what's going on in the cluster, what's happening in terms of work being done in the cluster, in terms of I/O, in terms of reads and writes, and utilization. This web page is actually, let me go back. Sorry about that. This web page is actually on the Elastic MapReduce when we start up the cluster. As you can see, we have the one line, we have the cluster itself by its name, the reference to the cluster, the name of the cluster, and its current status, which is waiting. But then we can start seeing below what's actually happening to the cluster. This is a nice thing to have up and running. It's almost as important as looking at the job tracker web page, which you have to basically find out the IP address of your cluster. Once you know that external IP address, you can then set that up to go after the cluster, and I believe the interface IP is 9,000. As we can see that this job took 1 hour and 17 minutes to load. Now we start getting into actually, now that our data at this point, we have data sitting on it, we had the raw data sitting on S3. It's now sitting on our cluster inside our H table that we've created. And we can actually go ahead, before we go into this, we're going to break out of our slide presentation, and we're going to bring up our cluster. And to make it a little bit easier to see, I hope that's large enough. We're going to walk into HBase Shell. HBase Shell is actually a JRuby shell script that allows us to interact with the cluster excuse me, on a command line basis. This is probably one of the basic tools that are out there. It's extensible because it is written in Ruby, so we can add features that aren't there. It allows us to do some minor cluster maintenance and some basic access to the data if we need to. One thing is those commands that are kind of important is status, which tells us how the cluster is doing. Well, that's the simple status. To show we actually have data out here, we'll do a little bit more complex, which is the simple, which talks about, again, tells us a little bit more about the data, about what's going on, the regions that we have. We have one server here, shows us what that server is. If we start to take a look at how many regions are out there, we see that we have 9 regions here, we have 9 regions here. If we want to go even more detail, status has what's called detailed. And we can start talking about the number of data stores out there and get more into the data and diagnostic information. While this is a little bit foreign to most people here, I'm just trying to show you that I have good access to understanding what my table has and consists of, just by looking at the status or looking at a list, which tells us the number of tables that we have. As we can see, that our tables essentially have quite a bit of data. If we go in, one of the things to show you is a quick little hint. In this job, we have a properties file, and in that properties file, we have to set the zookeeper quorum. Otherwise, we'll have trouble reading and writing from HBase. So here, to get that information, once we start a cluster up, we do a zk, I believe it's _dump. And while it gives us all the information about what's going on with Zookeeper, um, we actually can take a look and say that that Zookeeper quorum is IP 10, 155, 240, 226, EC2 eternal. This is the information that we need to put into our properties file so that we can read data from HBase. Taking a quick step back, because I know we didn't really have time to go into the components or structure of what makes up HBase. HBase really has the HMaster, which talks about where all the regions are and handles the maintenance. We have the region server, which handles the storage of data. We have this thing called Zookeeper that really isn't part of HBase. It's yet another Apache project which helps coordinate the information between all the regions. And Zookeeper runs in a quorum so that if when you start up the cluster, you can start up one or an odd number of these, that if you lose one instance of the Zookeeper, you may not necessarily go down. So as long as an odd number of the remaining Zookeepers are up, which is basically 1/2 of n plus 1, where n is the number of Zookeeper instances running, you're able to maintain and have the cluster run. And I realize that's getting into much more detail than you're familiar with. And again, this is maybe too much detail at a high level. Just wanted to give you an understanding as to one of the things we needed and why we needed it. Okay, so getting back down to this, we take a look. Again, list tells us what tables we have. And here, think big stocks are a table. We have another command called describe. And this gets into the schema of what represents this table. And again, in HBase, we start off with the name of the table. And the table is broken down into families or column families. And this is a way of storing like data so that they're stored together on disk. In this case, our name is Avro Stocks. We're not running a Bloom filter. We're not running anything out of the ordinary. Everything else is default. For example, the number of versions is 3. That versions talks about the number of cells within a column as to what to keep around. So if we update, every time we do an update, and I kind of alluded to this earlier in the presentation, we are actually running a new cell. And after 3 cells, the next update replaces the top one and the bottom one goes away. So we lose data that way. And basically, a cell is a point in time value of the data. So that as data is being written in, added to it, we have the ability to have some sort of consistency. If you want to take a look, and this is probably going to take a few seconds, there's another built-in command called count. So if I do count, and again, because this is a Ruby script, I have to put the values or parameters inside of quotes. And pardon me if I don't mistype this. As you can see, we're going through a count, and this is, again, a single-threaded running through the data. We could talk about really, as we go through at that nth number of row, for example, 200,000th row, we could see that the key is that value. That's the stock, and then that's the date of the stock. And that's how we actually store the data. If we look at the code, again, I urge you to look at the code after the presentation to take a look and see how simple it is. And as it runs through, this is again at the 700th, 800,000 rows. I believe there's 11 million rows in this system. Now I'm going to Control C out of this. It actually takes me out of the shell itself. What I want to do is, because I actually have the second program run, which is much faster, I'm actually going to show that running. And if I can, here we go. Basically, the invocation again is Hadoop jar. then the name of the jar, as we can see, is my HBase MapReduce. I'm sorry, is my HBase MapReduce map average high program. I'm going to run this, and it's going to go through and actually run the average high per year for specifically IBM, and I'm going to store it out on S3, and I call it SAH.out. Excuse me. So as you can see, we launched the job from the command line, and it sets up the MapReduce job. This is a very, very quick job. While we have all these different regions, because all the data for IBM is stored sequentially, it just happens to fit into one region. So we're going to have one mapper, and because we want all of our data into a single file at the end, we have one reducer. As you can see, the job is finished. It's now cleaning up. It tells me that I've gone through and processed, in order to process this, map output of 12,000 records, give or take. So we can start to see that it actually went through and did a lot of processing all within a very short period of time. If we want, we can actually go out to our cluster, and if we refresh this, this will show you that I just ran this job, and that this job, the successful, ran in 38 seconds. Sorry if I can get it right here. Looks at the finish in 38 seconds. We can see that that took that time to actually start the job, kick off the mappers, take that data, do a sync, do a sort, and traverse it, send the data out to a single reducer. And again, since it's such a small cluster, it doesn't really have a lot of network play. However, with the 4x large, you are on a 10 gig network, so the network latency is further reduced than from other systems. If we want to take a look at the actual results set, we go into my directory on S3 and allow me to refresh this. So it always takes a second or two. And this is the one thing about live demonstrations that always goes wrong. But by doing a quick refresh, you can see that we created the directory, SAH-OUT, for, I don't know why I called it that, but I just did. And we can see our results set is always going to be called part-r- and then some number. Since it starts with 0 in increments, we only have one file, one reducer. That's our only file. If I double click on it, it downloads locally here. I'm opening it up, and I can see, and again, I wish I had a way of increasing the size of this. Let's see if we can do that. No, we're going to have to do it this way. Well, actually, I don't have time to do it. You can actually, when you run the program, see this, that basically it's taking the average from 1960, 70, 80, 90, 2000, and 2010, saying the average stock price. And unfortunately, our application is really, really simple. It doesn't take into account the splits. So we can see that the average stock price in 1960s was $442 a share. Then in 1970s, it dropped down to $274. And since the 80s, 90s, and 2010s, it's been around 198, now 128. So again, it's just to show you a very, very simple explanation of how a MapReduce job will actually take data from HBase, take result sets, and write it out to S3. And if we go back to our slideshow, what we really haven't talked about or covered on this is some of the applications out there and why we'd want to use HBase. HBase can provide data directly out to end users' applications so that you can provide data in real time. At the same time, we can use HBase to store an index. So if we have a lot of data sitting in flat files on S3, and we want to then pull up a subset of that data for processing, we can then use HBase, connect to HBase directly without doing a MapReduce job, look for that specific set of files that we want, find out where they're located, and then take that URL of the S3 location, use that to pull the data out into a MapReduce job, and then have the MapReduce job read from S3, do the work that it wants to do, and then sends that data outside. I have a friend at a very large telecommunication company that is using Amazon and S3 to do precisely that, where they're using the HBase as an index or storage of the index to actually pull out subsets of data that they can work on. So in conclusion, HBase does allow for ad hoc access to data sets. We can fetch and use the method get to pull out a single row. We can use scan. In our example, we use a scan. We have a start row and a stop row. We can use it as part of a MapReduce job or a standalone process. We can use this for batch processing. We could use this for subjective real-time cases. And that is not so much that we're expecting instantaneous real-time space, but we can use it in what would be a reasonable amount of time that a person would be paying attention to the process. Definitely HBase works best when used within the framework. While it is theoretically possible to use HBase against any file system and run it outside of the framework, it is not recommended. We do use it with JRuby, Hive, and Pig, but primarily it's accessed through Java. HBase is still an evolving technology. It has, in the last 3 years since I've used it, it has grown exponentially in maturity, much faster than the relational databases have, but it's still something that takes a lot of time to master and can be very temperamental. The reason we like it is that it is in part of the framework. As a Hadoop framework, it allows us a lot more flexibility and ability to solve more challenging problems. For more information, obviously, you can reach me. My email address is here, and you can go visit the Think Big Analytics website. But then also, to learn more about Amazon, I suggest you go to the primary starting off site at Amazon's Elastic MapReduce, where they talk about their training, online training, paid training on site, or also the documentation. Thank you very much, and I hope that you have found this to be very informative.